Same issue here. Also still the process of waking up, so nothing better than this big white mug of black coffee. So, how should we start today? I was thinking maybe to have a little bit of a flow chart of the quote-unquote journey that we've done the last 5 weeks or so, because there's a lot of maths, there's a lot of physics. Sometimes it's hard to entangle what was the maths and what was the physics. Okay, so what I would like to do is just give you a couple of steps, how we went from the starting point to the point where we got here. And as I promised yesterday, today I'm going to give you the final one equation that combines all of electrodynamics. So, can you fill me in, Amy? What was our starting point?
Maxwell's 4 equations.
That is true, but we had even a point before that. Of course, it's
Bios of art.
Bios of art. Yes, there was an equation that told us how to calculate the magnetic field given. This is wrong. It should be 4 pi. I might drop these things to begin with, okay? That if you knew how much current there was in a certain situation, and then something like this. If you knew how much current there was in a certain situation, you could calculate what the magnetic field was and what direction this was pointing. This was Bios of Art's law, and I took that as a experimental fact. This one. To be really consistent with my previous notations, this should be called a J, because I reserved I for a line current, and this is a volume current. So there we go. And of course the integration is over the sweeping coordinate, which I always designated by a prime. And for the electric one there was a similar thing, which was Gauss's law. And Gauss's law told you what the electric field was given a charge at a certain position. And that was this one. Forget about the 4 factors, right? The mu0, the epsilon 0 we took for unity as of yesterday. And there's a number of 4 pi's here and there. But I really don't care about the 4 pi's today. This is really just how did we get from the starting point till the end. Now, just using these two, we constructed Maxwell's laws. So from these, just by doing vector calculus, we found these beautiful babies. I'm not entirely being correct right now. Let me comment on this in a second. This one is a direct rewrite of this one. This one is a direct rewrite, excuse me, this part is a direct rewrite of this one, only this part. This one comes directly from that one, just by doing the math. And then this one I took as a separate experimental fact, that if you wiggle a magnetic field around, you get a changing electric field. And this one then had to be there out of mathematical consistency. This is how we got there. So if you will, I put in 3 experimental facts. These 2 and this one. That's what we did. So these led to these. Remember the next step?
One thing I think it's not important, but I think you're missing the R squared in Bios of art and the cos
You
law.
are very right. Thank you. I was thinking about the potential expressions, but thank you. You're right. And of course it is important. Next step?
Vector potential.
Vector potential and scalar potential. I mean, to be sure, this is all the physics. All the rest of it that we have done, this we already got at the end of the first week, all the rest of it is just rewrite. Okay? So, electrodynamics-wise, we were done at this point, at the end of the first week. But yes, then the next step was that we could rewrite this into electric vector potentials and scalar potentials in the following way. Again, skipping just the math, but we found that if you would want to calculate the electric field, what you had to do was take minus the gradient of this thing phi, and subtract from that the time derivative of vector field, vector potential, and there's this here, but I'm being very inconsistent with my epsilon zeros and mu zeros. So if you don't see them, just check your notes, they should be there somewhere. My mind is halfway in setting into unity and halfway just out of muscle memory writing them down. Okay? So that was one, and you could calculate the magnetic field by taking the curl of the vector potential. This is what we did. We found that this is just a mathematical fact that you could do it this way. And then we derived that if these are not the fields that you're looking for, but these are the fields that you're looking for, what the differential equations for these fields should be. And we found that, and now I am purposely dropping the mu zeros and epsilon zeros, that the vector potential and the scalar potential both agree with the same differential equation, these two. Again, all rewrite, no new stuff. I secretly smuggled in here that you had the freedom mathematically to choose your gauge, and I chose the Lorentz gauge. For later convenience, let me just write down what the Lorentz gauge was. That is that you choose your scalar potential in such a way that it equals this. That was a choice you could make without changing the E fields and the B fields. So taking this Lorentz gauge, you can show that the vector potential and scalar potential obey these differential equations. And the beautiful thing was that we know the general solution to this thing, to both of them. So at this point we had all of electrodynamics, and at this point we have all of electrodynamics solved. What was the next step?
Retarded potential.
Of course, it was retarded potentials. In fact, it's already in here.
Yeah.
Because what Jocko did with you was show you how you would build in the time delay. And what he showed you was that you can build it in the general solution for these things, so phi and the A field, by changing the t coordinate by t minus r over c. So it's already built in there.
So these two formulas take into account time delay and time contraction?
Yes. Although the time contraction is not very clear at this point.
Yeah.
Okay, but the time delay is already built in. Again, let me re-emphasize. What Jocko did with you was he took these equations, he built in time delay, and then he showed by taking the derivatives that they already obey these equations. So it's already built in. So the retarded potentials are in there. Next step.
We did relativity, but in the notation? Other
Yes,
notation.
exactly.
Four
The
vector.
four vector notation and contractions and such. Now I'm not going to write that out all. The only thing I'm going to do is say how you can rewrite these into four vector notation. And for that we first had to show that these two together form a four vector, and they did. And then we used yesterday these two equations themselves to show that then these together also form a four vector. And this part, minus two time derivatives plus two space derivatives, itself is a contraction of two derivatives. So these two together in four vector notation would look like this. This part, the contraction of the derivatives, will take care of these two derivatives here, including the correct minus sign. That's what the Minkowski method does for you. This is a four vector, so I can write it as a four vector. These two together form a four vector, I can write it as a four vector. In other words, this whole thing that I have here is just a summary, a relativistic four vector notation summary of these two equations. And this is what I said yesterday. We've reduced our original problem to only one equation. I'm lying a little bit here because these are really just four equations still, right? For every, I should not have used mu. You see why?
Used mu.
Yeah, I've already used my mu's for my x's and my contraction here. And for a casual reader, somebody who would just come in and would only know about the contraction rules, he would say, wait a minute, I see a mu here and a mu here. Should these two be contracted, or should these two be contracted, or should they be contracted, all three of them, or something like that? So, again, muscle memory, I typically write my 4 vectors with mu's. To not confuse them with this one and that one, let's call it alpha. Back to my point, these are really just still 4 equations. For every alpha value, there's 1 equation. The 0 equation just gives you this one, and the 1, 2, 3 equations give you that one. So this is all a rewrite. So this is where we are. This is all what we did. That's a flow chart of the last month and a half or so. Now let's see if we can rewrite it further still. In order to do so, we have to know how you can take one guy's electric field and transform it to some other guy's electric field, and the same with the magnetic fields. And that's the exercise that we did the first 2 of yesterday. And well, I want to complete the whole set today. And once we have those 6 equations that tell you how the 3 E components of one guy transfer to the other guy, and the 3 B components of one guy transfer to the other guy, we have 6 equations. And those 6 equations I too want to put into relativistic form. I don't have to, because this already encapsulates all of electrodynamics, but it encapsulates electrodynamics in phi and in vector field, scalar fields and vector fields. What I would like to do is encapsulate all of electrodynamics in magnetic field and electric field. Again, I don't have to. Once I've solved this and I get my phi and my A, I can just use these two and get my E's and B's. It's just I want to have a formalism that skips this step, that gives you E's and B's directly. That's the idea. So again, no new physics, it's just rewrite, rewrite, rewrite. So this is what we were doing yesterday. We were finding the dictionary, if you will, for one guy's E's and B's to the other guy's. And I forget which one we did yesterday. I think it was, one was very simple, it was BX. And that turned out to be the exact same BX as the other guy, okay? So let's do it here. It's called a dictionary, as it translates one guy's language to the other. This is what we did yesterday. BX, one guy we found is exactly the BX of the other guy. And then was it EZ that we did. And I think it was gamma times the other guy's EZ plus or minus the BY of the other guy. Can somebody help me?
Yeah, it is.
Just BY?
Plus.
Gamma.
Yeah.
Plus gamma BY?
Gamma V BY.
V, okay, yes. Okay, good. This was it, yes? Now let's do the other ones. I'd like to go through all 4 of them just as a big exercise in learning how to deal with the 4-vector notation. Some of them are going to be simple again, some will require a little bit more work. We have 4 more to go. Have you built up a preference so far, as of yesterday?
EX?
Okay, EX. Let's put the whole dictionary here. Let's take this as the derivation part. Right. Well, want to do this together, or yeah, let's make an interactive thing. Some guys EX want to know my EX. What do I do?
So you need to prime all the things you need to prime.
Okay. How?
Um,
I have nothing to. I mean, I have an EX with a prime, and you're suggesting get rid of the prime?
No.
Oh.
I'm saying that you should put the primes of the things you need to prime.
Oh, yes. Okay, good. Yeah. Yes, that's of course what we're going to do.
I have a question. Do we always start with the standard formula, like the E is equal to derivation of
Yes,
E
because
plus
this
or
always
minus?
holds. Yes. In fact, in the second lecture, I showed you. We did it very explicitly that you can always write it like this.
Mhm.
And we use vector calculus. It had something to do with that the curl of a gradient is 0 and such. So this is generally true in for every person, for every frame, not because of physics reasons, because of mathematics reasons. Okay, we're really far away from everyday world if the mathematics would change from one guy to the next. Never thought of it that way, by the way. I mean, what we're doing in relativity is make sure that we have equations that work in all inertial systems, But of course, there's always this implicit assumption that the mathematics, just the rules of mathematics, are the same in all inertial systems. I see no reason why it shouldn't be, but I guess there's probably some philosopher out there who's thinking very hard about these things. Okay, but yes, we're going to take that one, because I think that will be your suggestion. And so that will be this. I have to take minus the gradient of the scalar potential, but I have to do it in x direction, which is just the ddx of that guy, and then minus the ddt of ax. I'm now firmly back into dropping mu zeros and epsilon zeros. And of course there's primes here, and then we're going to take your suggestion and Lorentz transform these. Because we knew this behaves according to a Lorentz transform, this one does, and these do as well, but by inverse Lorentz transform. All right, can somebody dictate?
It's gamma dx plus vdt. Sorry, ddx.
Yeah.
Plus, right?
Oh, yeah. Okay. So you went for the even shorter notation with the dx.
Yeah, I did that. Yeah.
Yeah. Well, let's do that from now on. Okay. dx.
You would do
Plus minus.
Plus, right? Because it's
Yeah.
contravariant.
Yeah. Exactly. Exactly. Oh, I love that you're using the right terminology too. Yes, it's contravariant. That's true. Okay. What else?
Yeah. Okay. Minus gamma dt plus vdx. And yeah, you can also transform.
Yes. Exactly. All right. So we've now transformed the derivatives. Next step, transform the phi's and the a's. Somebody dictate, please. This is not a test. I really don't know. Well, it is a test. I do know. Maybe somebody can tell.
Check it. So it's gamma phi minus v ax.
Yes.
Yeah.
Why is it a minus? I love the right
Because
terminology.
it's covariant.
It's covariant. Yes, exactly. Yes, it's a covariant four-vector. Now, I made a point yesterday that I'm not going to pursue the whole covariant and contravariant. There is a whole body of mathematics behind that we can easily sidestep here. It would just, I think, obscure the actual point. In general relativity, the point is much more pronounced. So there, I will make a point out of it. But for now, it is leave it. Yes.
How did you see that it's like covariant?
We haven't proven it yet.
Okay.
So this one, that this is this one here, that this is covariant. That we've proven yesterday that this one is covariant.
Mm-hmm.
I postulated that my ddx is contravariant, but we haven't proven it yet.
Okay.
And if we have the opportunity, I would like to do that today too. But it's of course it's a good question. We haven't proven it. I've just said that it was so. So you're right. There's still a hole in our whole argument. I think all the mathematical steps we've proven so far, except this one. So we still have to do that at some point. Let me just fill in this one myself, because if I'm not mistaken, this one goes as such, covariant, so it would be this. Okay. Now the steps are very similar to what we did yesterday. You just clean up the mathematical expression and then hope that you recognize what the e's and b's are of the other guy. Yeah, there we go. All the derivatives will not feel the gammas and the ph's, because the time derivative it doesn't feel, because we're going to assume that the two observers are moving with constant velocity with respect to each other. So it makes v a constant, and as a result makes gamma a constant. So the ddt's will not feel the gammas. Now the v's and the gammas were never functions of x to begin with, so it will also not feel the x derivatives. So as far as all the derivatives are concerned, the gammas and the ph's, you can just pull through them. I hate working this stuff out. Let's see, dx phi. No, we're going to do a little bit different. We're going to write down. Yeah, there's many ways to you can write this. I'm just wondering what the best way to do this is. What should we do? Should we group all the ax's together? Maybe that's an idea. And all the phi's together. Yeah, let's do that. Let's get all the phi's one expression. So here's one phi. Here's another phi. That's a minus. It's a minus. That will give you a plus. But with this minus, that's a plus again. So that's v squared dx. Fine. Yeah, that's this term. And this one, I think. You can already see what's happening here, yes? You see the gamma squared, and you see a 1 minus v squared. You already know that those are going to cancel each other out. So you already know this is going to be a minus dx phi. What else do we have? I see some a-axis. Yeah, let's group the a-axis. Somebody help me out? Get all the a-axis together. Let's be more clear. Let's get the dt a-axis together. Can somebody take that?
Just the same thing that you wrote.
I'm not sure if it's exactly the same thing, but you might be right. I've seen ax here. I'm going to collect dt a-axis. Here's one. Comes with a minus. With another minus gives you a plus. So that's that one. Comes with gamma squared and a v squared. So that should be this, I think. So that's that one. These two together, and there's also one here. Minus. Oh, yeah, you're right. Yeah, gives you exactly the same thing. So that would be minus v squared. Is it a v squared?
Yeah, it's v squared.
No, excuse me, I miss a v squared here. Right, that's that v with that v, that's a v squared.
Oh.
And this one, this dt ax does not come with any v's. So it gives you gamma squared dt ax. I'm doing this real time, so if I'm a little bit clumsy, please forgive me.
Alright.
And if I'm not mistaken, I see a gamma squared here, I see v squared minus 1. So that's minus 1, gamma squared. This is minus dt ax. We can already sort of guess what's going to come out, can't we? Because these two together, isn't that exactly what we call ex via this rule? So, getting ahead of myself, but I think this is minus, this is ex, this part. We still have some parts to go though, we haven't done the full working out of the brackets. What other combinations do we have here? Here. dt phi, how about those? dt phi is there as well. I think they're going to cancel out. The reason that I think so is because if I end up in my end expression with the dt of a phi, I will not be able to put it into e's and b's, because none of these two equations allow a ddt of a phi. So my initial guess would be no ddt phi's, but let's see if they cancel out. I see ddt of this phi with a minus gamma. Let's just write it out. Let's do it here. It gives you a minus gamma v dt phi. That's that one with that one. And I think there's another one here, which is exactly the same thing with the plus. These cancel out. Is that all, or are we missing one now?
Yeah,
That's all.
Which one?
dx ax.
Yeah, dx ax. Yes, you're
But
right.
it's gonna be cancelling out as well.
Yeah,
Right.
everything is going to be cancelled out. I think you're right, because this one comes with a gamma squared and a minus v, so gamma squared v ax plus. And here is v gamma squared, yeah, with a minus, so they cancel out. Okay, so there's another term, blah blah blah. But that means it's just ex. We've now found one guy's electric field in x direction is the other guy's. Another one. Let's do one more, just for funsies.
EY.
Sure. Okay. BY. Okay.
EY.
E or E or B?
E.
E. Sure. Okay. So EY. Any special preference for that one, or?
Just to complete the series.
Oh, yeah, you're right. Just out of symmetry or something. Yeah, yeah. Yeah, you have to be careful with these days with these gender issues. You cannot have two E translations and only one B. There's probably some B group somewhere in the world that said, wait a minute. It's called the B2 movement. Oh, I thought it was hilarious. Okay. Okay, BY. I'm sorry, this is funny as I get it on early morning. Hashtag B2. I love this. So, maybe somebody else can laugh about this after this one is over, this lecture. Okay. Okay, BY primed. That means that we have to take the A field, the curl of that thing, and take its Y component. And because we are in this guy's coordinate system, his X, Y, and Z, that means the nabla comes with a prime, and the A field comes with a prime. Okay. Let's see if we can do this by heart. The Y component of a curl. I never memorize these things, I have to do the calculation over in my head. The Y component of a curl. It's always going to be some
Z over X.
DZAX.
DZ.
X.
Yes, this is true. And here it's the opposite, yes?
XC. XC, not XV.
XZ, yes. There we are. Okay. Okay. Now do this whole transformation thing again. DZ. Primed. Has to be written as a DZ without the prime.
Just DZ.
That's just DZ. Let's leave this one for now. The X primed, of course, the whole Lorentz thing again. Inverse Lorentz gives us gamma dx plus v dt. So that's that. And we've now written the derivatives without the primes. Now let's now write the fields, the vector potentials in primes. Ax prime, of course, goes with the Lorentz transform, because we did our best yesterday to show that it is 4-vector v phi. And az prime, of course, is just az again. There we are. Clean up a little bit. The gammas are not felt by any of the derivatives, neither are the v's. And let's do some collecting now. One thing that I see happening is this. That's in there somewhere. Right? That's this one and that one with a gamma in front now. And this whole thing is by. Now there's still some leftover terms. What else do we have? Gamma minus gamma phi dz. Should be something like this, I think. And there's one more here, I think. Minus gamma dx. Oh, I'm messing up here. Oh, yeah, I think it's this.
Are you not missing the V?
Yes, and I'm missing a V. Thank you, that's that V. and also I wouldn't have gotten to the right end result. So this, I think, is plus gamma EZ. Oh, and a V. Gamma V, then what I see is the minus derivative of phi minus the time derivative of AZ, and according to this rule, that should give me EZ. And then I have another one of my dictionary. Yeah.
This mathematics, has it been proven, like the multiple?
What do you mean proven? The mathematics has been proven? Yes.
Yeah, no, but like in experiments.
Yeah. Oh, absolutely. Yes, extensively.
How did they do that? Like, how did they? Because like you have to do like with high speed.
Yes.
How did they measure?
Oh no. They can do this. For instance, if you have a small particle, like a nuclear particle, an electron or so, and they shoot it through an accelerator. I have to be careful now. You have to make sure that they go with constant velocity through the thing. You're allowed to describe this particle if it's not going with constant velocity, if you yourself are in an inertia frame. But if you make one and it goes with a constant velocity, then you're also allowed to transform yourself onto that particle and then use the same rules. Now for that particle, if that particle is flying through, say, an electric field, in his frame you will now see also a magnetic field. And that's just experiments that you simply can do. And of course you're right, you can only see these transformations really well till the gamma becomes sizable, so that means high velocity, and that sort of requires you to have particles that have very small mass. Because of that rule that we derived before, that the energy that you have to put into something to make it go with a certain acceleration is this equation, right? We derived that last week. And of course, for n's, this is a very a big number because of the c squared. So this is why you have to do it for very small particles.
Now that you say it, like if you, for example, have like a really low speed so that the gamma is 1,
Yes.
then you have anyways by is like by plus.
Yes, that's very true.
So it's anyway.
No,
yes, plus electric field.
Yes, you're right. I mean, you would, yes, but this we already knew before we did the calculation. That's the prime example that I always use. Taking Chi again as a charged particle. Me walking past him, even at low velocities, will now give me a magnetic field.
Okay.
And on top of that, because of high speed, you get a gamma times that thing. But even at low velocities, you would still get that. Yes. All right. Now, perfect. Now, I wanted to do all 6 of them, but I really do feel that it's now going to be a rehash, these last 2. So let's just take the other ones and just write them down. You can easily prove them for yourselves. Do you have them, by the way? Because I'm just going through my notes. Not sure if I can find them immediately. Yeah, there they are. Bx, x, yes. By, we have Ey. It's just going through the same steps should give you this. Minus Bz. And what's the last one? Which one are we missing? The Bz. Bz should give you gamma Bz minus gamma By. This is the complete dictionary. Now, I hope you see that this wasn't very hard work to get there. I mean, it takes you a while to get the materials, the raw materials to get these things, but once you have them, this is now an easy step. I mentioned yesterday the book derives these things as well, but they do by thought experiment. Right, to take a capacitor or something like that, or a coil, and they say, well, in this frame it looks like this, and in that frame it should look like this, blah, blah, blah. That's fine. Except that I prefer to do it from the mathematics, and not from this one particular example, and then promote the results as a general rule. We have now proven the general rule. The results are of course the same, so if you want to read it in chapter 12.3, go ahead. I mean, it's still good physics. So there we are.
Okay, so I'm moving along and towards an electric field with a y component. Now that I'm moving, the y component of my electric field is reduced but the z component is increased?
Which one are you using now? This one?
E prime z and E prime y.
E prime z. Yeah.
So the z component increases and the y component decreases?
Yes. You look.
So say the electric field is pointing in this direction,
Yes.
the y component will decrease and the z component will increase?
Yes.
Why does that make sense? If I just start moving towards it, it like curves?
I'm not sure exactly where your question lies. I mean, if you do the math, this is what comes out. But why would that be surprising? Let me reverse the question. Why is that an issue?
In my head, it would make more sense, say, if they both increased by a certain amount, or if they both decreased by a certain amount, since they're both directions which we're not traveling in. And so we've been treating them as the same up to now.
Would this solve your problem? At the moment that you have your E fields and B fields, ultimately the only thing that you will be able to measure is what force a particle feels and in what direction the force is, yes? So, actual physics-wise, experiment-wise, you're only interested in what the resulting force of the whole thing is.
Yeah.
The force that your particle will feel is its charge times the electric field, which, when you go from one inertial system to the other, all of a sudden changes directions. But that's not all. Will also be this. So your E fields, if you go from one guy's coordinate system, will change directions. Your B field will change some directions, or its components will change. But this will also have a change of direction. Now all these combined effects mop each other up.
Okay.
So I fully understand that the E fields and the B fields, they change direction. It feels sort of awkward. But my claim is that because of this changing of directions as well that you have in the actual forces, you will ultimately get the same result.
Okay.
Okay, so that was that. I'm going to make a claim. I would like to see if you can prove that. We now have all of this applied to the electric fields and the magnetic fields. I'm going to introduce a new thing. It's called a tensor. Now, let me immediately say that the word tensor here is used somewhat differently than the word tensor in other contexts. A tensor, well, very hand-wavingly put, is this mathematical object that has not one index, but multiple ones. Now, just as not everything that has one index, a combination of four numbers in a column, constitutes a four vector, not all combinations of numbers constitute a tensor. Not all matrices, which is a combination of multiple numbers, are tensors. Just like for a vector to be a four vector, a combination of four numbers in a column to be a four vector has to obey certain mathematical rule, the same thing applies for tensors. Block of numbers, but only if they apply a certain rule, this is when you call them a tensor. Now, the distinction that I want to make here is, the way that I'm going to introduce a tensor is I'm going to give you a very relaxed rule that they have to obey. This block of numbers has to obey this particular rule, and then in this context we were going to call it a tensor. In general relativity, you will find that the same applies, but the rule is more strict. The mathematical rule that the block of number has to obey is a more strict rule than we're going to do here. So call this a relaxed version of a tensor. You don't ever have to worry about the general rule, the more strict rule, unless you're going to do general relativity. Okay, so within this context, if you're not following what I'm saying now, forget everything that I said. Just call this thing that I'm going to write down a tensor. And at the moment you're going to do some course that gives you curved space-times, remind yourselves that there was some more strict rule that you have to apply. Otherwise, forget everything that I said now. The thing that I'm going to do, I'm going to introduce this tensor to you. It's called, this thing, two indices. So that means it will have rows and columns. Isn't that just a matrix? No. Not every block of numbers is called, that you would call a matrix, is a tensor. In this case it is. These are not, these are the components of that thing, the elements. I never know these things by heart, so I have to get them from my notes. marking Z's left and right here, C's, because you can immediately tell, in order for things to be in one matrix, they all have the same unit, and B's and Z's and E's do not have the same unit. So that's because there are some C's missing here and there. There you go. This is the thing. So it's a combination of the E components and the B components. And this thing we call the Maxwell tensor. Now, this is just a block of numbers. In order to make it a tensor, it has to obey the following rule. Suppose that I go to some other guy's coordinate frame. That means the E's will change. The B's will change as well, exactly according to the dictionary we derived ourselves. But it means this whole thing, tensor, will become a different thing. All the EX's, okay, those are going to be E's, they're going to be replaced with the other guy's EX's. All the BY's are going to be replaced by more difficult BY's. So if I take the components in my measure tensor and I will go to yours, it will be completely messed up. Okay? Now that's not an issue per se. By definition, a tensor is that the transformation between my tensor and your tensor. Well, let's see if you can guess what it is. If I go from my 4 vector to your 4 vector, what do?
Lorentz.
I Lorentz transform. And yesterday I wrote it like this. I said, well, if I go from mine to yours, and I know that this is a 4 vector, then I have to squeeze a Lorentz matrix in between, yes? What would you guess I would have to do here?
Maxwell tensor.
Yes, Maxwell tensor. Okay, there you go. What else?
The Lorentz matrix again?
Yes. But note that in order to make one index turn into the other guy's index, I need one of these matrices and one contraction. But I have two now. Gives us 2 Lorentz matrices. And you have to be ridiculously careful with the indices here, because as you can see here in the case of the 4 vectors, there's one here and there's one there, and those have to be alike. So let's take the beta here and make that the beta there. Let's call it alpha here and the alpha there. Here's the mu and there's the mu. It's really just applying this rule twice. For all of the indices I do that this once. Now again, in relativistic electrodynamics, this is what defines a tensor. Every block of 16 numbers that obeys this rule is what we call a tensor. Making the same comment as before. Unless you go to general relativity, then the rule is more strict. Then you find there's a rule like this, of which this is only a special example. So there's a more general rule for tensors, but for our context, this is what is the definition of a tensor. Now I have this thing now, this big block, that I say is a tensor. I introduce this f mu nu with this weird combination of b's and y's and minuses and such. My claim is this is a tensor. Want to try to prove that? All right. I'll report back to you in, what, 10 minutes or so? See if you can try this out. So the only thing I'm doing is I've introduced this crappy thing here. Well, it's not a crappy thing, but for you it might be a crappy thing. Why would you introduce such a thing? And my claim is, well, let's first prove that it is a tensor. And once we know that it's a tensor, we can use that property for some later mathematics. So that's the question. Can you prove that this rule is applied here, that works? Prove that f mu nu is indeed a tensor. things going? That sounds like people who are not getting it. With some difficulty.
Is it possible to do it by matrix multiplication?
Yes.
Yeah. Oh. So I think I'm getting wrong results.
Okay. There's two types of getting stuck. One of them is, I think I'm doing it correctly, it's just that my result is different than what was expected. And
Yeah.
there is the kind, I have no idea what I'm doing.
No, my results are different than what I would expect.
Okay.
How do you know what to expect?
Yeah, you should get those things. Like,
Oh yeah, you
yes.
should get it back. Yeah, it doesn't look like that.
Okay.
right? Like that's the whole thing we should get.
Yes.
Yeah.
That's true.
We can try. Should I just do maybe one of them, two of them? Of course, there's 16 of them, so it takes a while to do all of them. But just for overview's sake, let's do one or two. And then the other ones go in a similar manner. Alright, let's see it here. I'm anticipating I'm going to need a little bit of space, so if you like vertical or horizontal? Let's go horizontal, so I have everything on one board. Okay. Okay. Well, suppose that I would like to know what my, well, maybe you can give me one. What new value shall we take? Well, there's 16.
0 and 0?
0, 0? Sure, okay. Well, not a big fan of this one. Because that is 0.
Yeah, but I don't get a 0 there. So
Oh, really?
yeah,
Oh, that's interesting.
that's
I
all.
do get a 0, but I think I messed up my sign somewhere. But I do get a 0.
Okay. So it's deliberately that you're choosing this one, the 0, 0 component. Okay, well, let's see what happens. Okay.
And then I fixed it.
So I would like to know what my 0, 0 looks like expressed in your 0, 0. And according to this rule, that requires 2 Lorentz transforms, one for each index. My mu has to be 0. This one is the one that I'm contracting with. Nu has to be 0. 0. This is the one that I'm contracting with. B alpha. So it should be this. There's 2 contractions now. I have to take my beta to be 0, 1, 2, 3, and I have to take my nu to be 1, 2, 3. So this is 16 terms in total. Fortunately, hopefully, a number of them are going to be 0 immediately, so we don't have to write everything down. So let's see. Let's put the Lorentz matrix here for quick convenience. Gamma minus gamma b 0, 0, gamma b minus gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. The saving grace in contractions is that the matrices that you're contracting with usually consist of many zeros. So of the 16 terms, many are going to drop out. And same here. Let's do the beta contraction first. Let's do it in a quick way, okay? So if I look at the first row of my Lorentz matrix, I see that there's only 2 columns that have non-zero. So those are the only ones, the only nus that I have to be concerned with. Excuse me, they're called beta here. Beta 0, that's this one, and beta 1, that's that one. So if I do that, I would get 0 and beta 0, which is a gamma. This I'm going to keep for now. That's a contraction for later. And then this beta is again 0 alpha plus the other beta that gives us a non-zero will be this one, which comes with a minus gamma v, and then it will be 1 alpha. I think this is it. This is the contraction over the betas. Feel free to write it out in full, but quick glance at the Lorentz matrix and you know exactly what terms you have to take into account instead of all 4 or 16 or so. Now there's still one contraction to go, that's the alphas. Again, I'm looking only at the first row, 0th row, and then I have to look at all the columns that have non-zeros. And those of course are exactly the same ones as the beta here. So that will be when alpha itself is 0, that will give us another gamma. this. Okay. Minus gamma v, both come with a square again. Oh, this is wrong. Should be like this. I think this is correct. Agreed so far? Andreas, did you have that too?
Something like that, yeah. Because my approach was getting the Lorentz matrix multiplied by itself. I don't know if I can do that.
Carefully, I'm saying yes.
Like matrix multiplying it?
Yes, but you have to be careful. This discussion that Chai and I had in my office a week ago or so. These two are not multiplied with each other.
Are they not?
No, they're not. Because for matrix multiplication, just generally speaking, what you do is you take one matrix's row,
Yeah.
and you do it with the other matrices column.
Yeah.
And if you think about it carefully, it's going to be a contraction of the first row and the first column, because you're going to take the 0 of the 1, the 1, 1, plus 2, 2, plus 3, 3. Note that there is no contraction between these two matrices. In order to have these two multiplied with each other, they would both have the same index. They don't.
Okay.
So these two matrices do not feel each other. So it looks like a matrix multiplication because you have two Lorenzes next to each other, but there's no contraction with them in between them.
Oh.
So it's not a matrix multiplication.
So, what were you thinking about when I said matrix multiplication here? Like, what's the way of doing it with matrix multiplication?
That I thought you meant this contraction, the beta with this one, and then you have a matrix, Lorentz matrix, and the Maxwell tensor matrix, and that matrix multiplication. I thought that's the way, that's the one that you meant, I thought.
Oh, so is that like doing first the multiplication with one of the contractions and later again with the other construction?
Yes.
Okay.
In fact, that's what I'm doing right here.
Yeah.
So that was a good point. In fact, I had a blind spot for this, and until Chai came along last week and asked pretty much the same question in a somewhat different context, but it basically came down to the same question. I said, no. Not every time that you put two Lorenzes next to each other, that means it's a matrix multiplication between the two. That's only the case if they share one index, so you can do a contraction with them. And here they don't. So it looks like a matrix multiplication, but it isn't. So I'm guessing what you did was matrix multiply these two together, and then that resulting matrix apply on this thing.
Yeah.
So that doesn't work.
Yeah, I see. I see it doesn't.
Yes. But let's see what we do get now.
Yes.
This is what we get if we do the contractions.
Gideon?
Yes.
What about the case of f10 and f01?
What about
Is that not included in the equation?
No. No. 0, 1 and 1, 0. I'm not sure why. Why should they follow?
I mean, it's in front of the alpha, isn't it?
Yes, you're very right. Yes, yeah, thank you. Yeah, I think you're right. I think I missed two terms. I think so. Let's do it again. This was correct. This part.
Yes.
Okay. Here's why they did the contraction over the betas, and now I'm going to do the contraction over the alphas. Yeah, you're exactly right. This was my bad. Yule's point was that the alpha has to be either 0 or 1, right? Those are the only columns in the 0th row that give you non-zero. So that means that alpha has to be 0, that will give you this one, but it can also be 1. And in that case, it gives us minus gamma v. The what already was a gamma, gives you gamma squared. And then there's f10. That's it, yes?
Yes.
Okay, good. Thank you. And then this one, another contraction. Alpha is either 0, 0th column. That gives us another gamma. f10. Agreed? And what else is there? When alpha is 1. And that would give us... No. Making a mistake here. Just a second.
Why is the v erased?
Yeah, that was a mistake I was making. So, okay. Gamma v, nu is 1. Nu is 1, that gives you 0, 0, it gives you gamma squared. Gamma squared. And there's a minus sign wrong there, but let me match that up in a second. There's a minus sign. Which minus sign is that? doing these two. Alpha is 0, gives us 0, 0. That gives us a gamma with that gamma and a minus sign. This is correct. If alpha is 1, then I get 0, 1. 0, 1 is with its own additional 1. Okay. And then there is still a v.
V squared, is it?
And here's v. Yeah, that's a v squared. Yes, thank you. I think this is it. Now let's see what we have. It's interesting. These two cancel out.
Not exactly.
Why not?
One is the negative of the other.
Yes.
They become 2 times of itself.
No, because it's minus minus, and because one is negative the other,
All right.
they get an overall plus and they cancel each other out.
Yes.
Right? If you look at this thing, it's what we call an antisymmetric tensor. If you replace mu by nu, you get minus itself. Right? If you go to 0th row, first column, you get EX, but if you go to first row, 0th column, you get minus EX. So every time you replace mu and u in their values, you swap them, you get a minus sign. That's just the way that I wrote this down. Now here is exactly what we have. I swap my mu and my nu. Right? My row becomes my column, and my column becomes my row. That gives you another minus sign, and then they cancel each other out. So these two together are 0. So ultimately what I end up with is this.
Which is 0.
Which is 0, because f00 is 0 and f11 is 0. So ultimately what I find is that if in my inertial frame my 0, 0 component of my Maxwell tensor is 0, then it is in everybody's. So I think your confusion was with the matrix multiplication. Okay. Let's do one more. Any preference? And let's not go for one of the 0 ones. Still no preferences for magnetic fields and electric fields?
You had my choice.
Okay. Now, honestly, somebody has to tell me. I'm too lazy today to pick one myself. Which one?
F23.
F23. Okay, let's do that one. Can I erase this? F23.
So now it's the moment I decide whether I'm going to do it by the whole matrix.
So 2, 3.
Or by that.
So that's the matrix model. Oh, excuse me, should have used that word. That's the contraction. There it is. Well, let's go through them. Let's start with the beta contraction first. Beta is allowed to be 0, 1, 2, 3, and then add everything together. But I already can tell that if I'm going to look at my Lorentz matrix and I'm going to go to the second row, 0, 1, 2, there's only going to be one term, one column that gives us a non-zero, which is the second column. So that means the only beta that will give you something is beta is 2. So beta is 2 is the only one that gives us a non-zero contribution, but that then says, this I'm going to leave for now, that beta has to be 2. So that's this. Okay, one contraction is done. You see how quickly you can do these things if you just look at the matrix first? I mean, you're also free to just write out all 4 terms and then read off what the values are, and you also get the same result, but you can go a lot faster. There's another contraction over the alphas. Alphas can be 0, 1, 2, 3. I have to look at the third row in my Lorentz matrix. 0, 1, 2, 3, third row, and the only non-zero contribution comes from the third column. So alpha has to be number 3, and that value is 1. So it gives us 2, 3. Look at this. My 2, 3 component is going to be exactly your 2, 3 component. This is what I find. If I measure what in my Maxwell tensor what the 2, 3 component is, and I ask you what yours is, you and I will agree on what the value is. It's going to be the same value. What is 2, 3? in electric fields or magnetic fields?
Minus bx.
Minus Bx. Let's see.
Very
Second
easy.
row, 0, 1, 2,
Oh, I did it wrong.
Bx.
Bx, yeah.
So apparently, one guy's Bx should be my guy's Bx. Isn't that exactly what we already had?
I thought nu was columns.
No, mu is columns, yes. Well, depending on how you wrote it down, you're free to call the columns and the rows in any symbol that you want. In my case, they were called mu is row, nu is column.
How is that bx? Shouldn't it be bz or minus bz?
There's no dz's.
In the f in Maxwell tensor.
Yes. What about it?
2 3s, isn't that?
0, 1, 2, and then the third column. 0,
Oh,
1, 2.
in the way of, okay, I was like with 1 2 3 4, not with 0 1.
So what we have found now is that indeed, if this is a tensor, I get exactly back this rule. Right? Now, my claim was that indeed this must transform as a tensor. That was my claim. That is what you had to prove. Now, one way to prove it is to show that if you apply the tensor rule to it, you just assume that it is a tensor, and it gives you back something that is correct, then apparently your assumption was correct. It indeed is a tensor. I've done this now for 2 of the terms. Now, my claim is that if you do this little trick for all terms, that's 16 of them, so you know, it takes you an hour or so just to do all of them. Well, maybe a little bit less, maybe 20 minutes or so. You will find that all the f's primes are connected to the other f's in the way as if it was a tensor. And how do I know? Because they always agree with the Maxwell equations. Conclusion, this assumption that it transforms like this is indeed correct. Conclusion, f mu nu really is a tensor in the mathematical sense of the word. Let me repeat that logic again. I wrote this thing down like this. I assumed that it was a tensor, so that this rule applies. I apply the rule and I find exactly my correct physics back. And because this is correct, that means my assumption must have been correct. So f mu nu is indeed a tensor. Now, why on earth would you write something that you already knew in a new language? Well, it's what we've been doing the last few weeks or so. And that's because I promised that this equation you can write in terms of the Maxwell tensor in a beautiful, beautiful way. Can I erase this?
Let's go. Let's go.
Let's continue here. Here's another claim. Suppose that I take this thing that I call a tensor, that we now know is a tensor. And you know what? Let's take its contraction with a derivative. Now, why on earth would you do that? Claim that this is exactly this. That's my claim. That once we now know that this is a tensor, I say, well, take this tensor, take its contraction with the derivative, that's this thing. My claim is gives you back exactly the 4 vector for the charges and the current. In other words, that's this equation written in terms of a tensor.
So that's the equation.
That is the equation, yes. Now, do you think that there's any difficulty in proving this? How many equations are there here, if you look at this? With the indices, you always get the impression there's only one equation. It's typically a number of them. How many are these? 4. For every new value, there's one equation. How many terms are there on the left-hand side?
4.
There's 4. The contraction over mu tells you you have to take mu as 0, 1, 2, 3 and add everything together. So this is really shorthand for 4 separate terms. That's because of the contraction over mu. And the fact that you can choose mu to be 0, 1, 2, 3 gives you 4 equations. So it's 4 equations where there are 4 terms on the left-hand side. Now, my claim is that this reproduces all of electrodynamics. All of it.
Sorry?
This reproduces all of electrodynamics. It's all in there. Well, there's a caveat, but let me get to that in a second. How about this? How about we just take the 4 new values and just see what happens? My claim is you will get back exactly your Maxwell equations. In other words, it's exactly equivalent to what we already had.
Let's do that.
Let's do this. Okay, preference for news. There's 4 news. I'm going to do 2 of them. Preference, 0, 1, 2, 3.
3.
3, sure.
Good.
Okay. So this is a claim, yes, I haven't proven this. My claim is, this is, again, all of electrodynamics. Little caveat, let me get to that in a second. And we're just going to prove it explicitly. 3 was the preference. Okay, well, let's see, 4 equations, let's see what happens if you take the third of these. That means the mu, f mu 3, should be this one. Let's make this an interactive exercise. What should I do now?
Go from 0 to 3 to the
Yes. I agree. Let's go from 0 to 3 of the contraction because of the mu. Let's be a little bit clever here, right? Instead of writing down all 4 terms, mu is 0, 1, 2, 3, and add everything together, maybe we can already see which ones are not going to contribute by looking at the Maxwell tensor. The third, which one?
F33.
F33, F33, that's this one. This is not going to contribute. The other ones are. So mu has to be, mu has to be 0, has to be value 0, 1, 2, not 3, because that would just be the derivative of 0, which is 0. So what I find is that the 4 terms in this particular case happen to be only 3 terms. This. Can somebody help me read off what the values are?
DDT.
Yes. So shorthand, we just call this dt, yes? And F03, what's that?
Easy.
Okay.
DX.
Dx, thank you. F13
Minus by.
and B1, B1, 3. By. Yeah, okay, yeah. I heard B1, but By, yes. And the last one, dz. This is 2, so that's dy. F23.
Bx.
Apparently is minus J3, and that's the Z component of the current, yes? Does this look familiar? Does it look like one of the Maxwell equations, maybe?
Yeah.
Which one? It looks Maxwell-y. There's derivatives of
The final equation?
yes. It looks sort of like this because there's a j in there, but also there's a time derivative of e, which we have here. So yeah, it looks like it. But this is three components, yes? This is a vector. And this is not a vector, because it's all in components, so it's all scalars. So which of the three components is this, of this equation? You think this is? I think so too.
Basically dx, dx by dx
Yes.
by dz, that's the curl of.
Exactly. Remember this thing is a curl. I'll just be a little bit careful which curl it is.
C, right?
Yes.
Z component.
But is it plus or the z component, is it minus or plus the z component of a curl?
Plus minus, I think. Because usually you have dx by minus.
No.
C by
AY
plus.
should be positive.
No, it's the other
Is
way
the
around.
x
Or
supposed to
BY
be
should be
first?
positive.
It is a z.
Yeah, it is.
That I can tell. I'm just wondering about the minus sign.
Dx first.
It's a dy. Yeah, this is correct. I think it's plus. Well, let's check. Any vector is. I always forget these things. It's one thing I've never learned by heart. Curl. I always have to derive it myself, but I think it's this.
So it is the minus.
So it's this, yes?
So
This
it's
is the curve.
So it is the minus. I think.
Yeah, it is.
Yes, it is minus. Okay.
There's a minus in front of the first.
Well, what I find is dy bx with a plus, and in a curl it's with a minus, so I need an additional minus.
No, I mean in front of the t.
I don't understand.
Is there supposed to be a minus in front of dt's?
Yeah, should there be a minus? F03. 0, 3. I don't see why there should be a minus. Oh, is that because of the contraction? No.
Minus?
No. Contraction just means take the value for mu, for mu, and add everything together. The only reason that why there could be a minus is because there's a Minkowski metric in between. There isn't. So it's all pluses. Now let's see what we have. What we have here is that if you take the curl of your B field, then it should give you back the current, and this one goes over there, this one goes there, plus, there's that, which is the fourth Maxwell equation. Well, it's one component of the fourth Maxwell equation, it's the z component of the fourth Maxwell equation. So apparently, this thing, at the very least, gives you the third component of the fourth Maxwell equation. Now my claim is that if you take mu is 2 and u is 1, you get the other two components of the fourth Maxwell equation. Right, this is an exercise you can do for yourself. If you make mu is 1, you get the x component of the fourth Maxwell. If you take mu is 2, you get the y component of the fourth Maxwell. So, conclusion, if mu is 1, 2, 3, these combined give you the fourth Maxwell equation. Let's do nu is 0. Any guess what that's going to give us? Which one?
The second equation.
The second, first?
Oh, yeah, the first.
It's going to give you the first. But we can just check, right? So let's do this. So this conclusion that we have reproduced the full fourth Maxwell equation in this shorthand notation. Yes?
What happens if you put instead of mu, the mu, like the I don't know how to pronounce it.
This is mu. This is mu.
Mu, yeah, if you take instead of mu.
As in, if you replace this by mu?
No, because like you said, like if you take mu, it's like 1, 2, 3, you get the fourth Maxwell equation.
Yes.
And if we take the mu, I want to choose.
Oh, no, we can't.
Okay.
Because the notation that we introduced yesterday tells you that you have to take mu 0, 1 to 3 and add everything together. You have no freedom in choosing what it is.
Oh.
It's a notation thing.
Okay.
If you have a mu upstairs and downstairs, that means mu has to be 0, 1 to 3 and add everything together. Now in that sum you have no choice in choosing your 0, 1 to 3 because it's all of them already in there.
Okay.
Now the nu does not come with another nu, so there's no contraction, so that means you're free to choose that one. So you can only choose your mu's. The mu's are all given a value by the contraction. Let's do the 0 one. Can somebody already see a problem looming in the distance? How many equations do we still have?
3.
We have no, as in 3 Maxwells. Well, no, excuse me. It was my fault. Let me rephrase my question a little bit more accurately. How many Maxwell equations have we now accounted for?
Oh, yeah, 1.
Only one.
Half.
And how many more mu values do we have?
1.
Yes. So we have one new value, nu is 0, and we still have to account for 3 Maxwell equations. But there's an issue there. This is a caveat that I said before. We'll get back to it. Let's do the nu 0 one. We have to do the, oh, this is wrong, this is a mu, and this is 0. Let's do the contraction over the mu's. So mu is 0, 1, 2, 3. So no choice in choosing your mu's. You have to choose all of them and add. Let's be a little bit smart. We have to look at the 0th column, so that's that one. And take all mu values that give us non-zero, which I think is mu 1, 2, 3. So take mu 1, f1, 0. So that's this. This is the contraction. And now let's read off what the values are for the f's. Well, you can just see what it is, yes. I mean, I can already hear you say it. f1, 0 is minus ex. And d1 is dx. So I get the x derivative of the x component of my E field. With a minus. The minus comes from here. And what I have here is f2, 0, which is minus by. And I have to take the y derivative of that thing. And so on. So you get this. And if I'm not super mistaken, this is divergence of the E field with a minus sign. That should be equal to minus the 0 component of my current. Yes?
I think there's a mistake somewhere because the EZ should be EX.
Should it?
According to this.
3, 0.
Well, it's EX on the board, but maybe it's supposed to be
Yeah.
Z.
Oh, thank you. Oh, you're right. Yeah, yeah. Oh, I have no idea where that came from. It was, yes, thank you. Thank you so much. Yes. Okay, thank you for correcting that. Then this is correct. This is EZ, yes. And this, summarized, is just minus divergence of the full E vector. And according to my claim here, that should be minus the 0 component, the nu is 0 component, of my current 4 vector. Do you remember what it was, the 0 component?
Rho.
Rho, with a minus. So apparently all of this should be equal to minus rho. In other words, the divergence of the electric field should be your charge density. That's the first Maxwell equation. That's the first Maxwell. By the way, I'm not proving that the first Maxwell equation is true, right? The only thing that I'm proving is that this is shorthand for at least 2 of the 4 Maxwell equations. The first and the fourth. Yeah, but we ran out of news now. Yet we still have 2 Maxwells to go. Huh. Sucks to be us. We've ran out of opportunities with our Maxwell tensor. So I've now introduced another tensor. This is called the dual Maxwell tensor. You can play the same game with this thing as we did with the F. First, you have to prove that this is indeed a tensor, that the G mu nu is again a tensor. Now you know how to do this. You know what the rule is. If this is a tensor, then that means it has to transform as a tensor. That means with 2 contractions with Lorentz matrices. My claim is, if you try to use this rule, this one, you assume that this is true, and you just try this, you will find these equations. In other words, this indeed is also a tensor. So G mu nu is another tensor. And again, some combination of bx's and ez's with minuses and such. So skipping this huge step, you can prove for yourself that that is a tensor. For funsies, let's take the contraction of this new dual tensor with the derivative. I claim that that is 0. I have 4 more nus to play with now. That's good news, because I was missing 4 equations. Wait a minute, we're missing 2 equations, the second and the third Maxwell equation. Yes, that's true. But this is a scalar equation, this is really 1, and these has 3 components, the third one. So these 2 together are 4 components. This thing also has 4 components, u, 0, 1, 2, 3. Claim. If you play this game again, u is 0 and u is 1, 2, 3, you will get exactly this one and that one. Now this is an exercise you can easily do for yourself. So that means that the missing Maxwell equations are mopped up by this equation. Now this you can easily prove for yourself. Prove that G mu nu is a tensor in the way that you also did for F. My claim is set is equal to 0 and it gives you the remaining 2 Maxwell equations. Let's wrap up. This was the flowchart of the whole lecture series. Okay. This one, in terms of the Maxwell tensor, is shorthand. You can also write as
You said it would be 1 equation.
yes. So was I lying or what?
It's the dual. Can you just add the 2 equations together?
I love that idea. Yeah, as it is.
Much better.
Yeah. Okay. I'm happy with that. Here's your 1 equation.
Yeah.
Okay, great. I was going for a different argument because I knew that this question was coming, of course, right? And that is, do you remember that some of the Maxwell equations were just mathematical rewritings of the ones we already had?
Yeah.
Right? the way that I put it before was the information of the E field and B field are, for historical reasons, scattered over 4 different equations. So that means part of the information is in one equation, part of the information is in another equation. The prime example for myself though is this one. That if I want to calculate what the B field is, say, I have to take 2 equations into account. That's sort of messy. It's not wrong, but it's messy. But fortunately, we found by our mathematical machinery here and there that this one already accounts for both this one and that one, or the first term of this one. So what is my point here? My point here is that this happens to be a really messy way of writing everything, scattered over multiple equations. That if you would have written down it in a much cleaner way, you wouldn't have needed the other equations. That's very much the same here. This one gives you 2 of the maximum equations, which already contain all the information, and the missing maximum equations are just rewritings of those other ones. But I'm happy with this result too. There you go. Here's the full 1 equation that you need. Yeah, I like that. Actually, Scott, I'm very happy with that. You know what? Let's make this our final conclusion. All 4 maximum equations are encapsulated in this one. So take this tensor, take that tensor, add them together, call it the Scott tensor, the Armstrong tensor. Okay. In fact, we can no, let's actually do that. Here's the S tensor, and it's just the addition of every of the single elements. So what will be the 0, 0 component?
0.
Okay. There you go.
Prove the Scott tensor in the example.
Okay, well, it's going to be a long ride, but well, etc. Okay, so we found all of electrodynamics is all encapsulated in taking the derivative of the Armstrong tensor and setting it equal to this. There we go. That really is the final conclusion. I cannot clean up the theory any more than this. Now, why on earth all this rewriting? We've made many arguments for this before. One of them was that the solutions to these equations in terms of the potentials are a general solution that I've already given you. So you've already solved it for everything, whereas it was much more difficult from the Maxwell's immediately. Now, so I mean, there's a very clear point to write it in terms of potentials. Now, why would I write it in terms of these things? That has to do with special relativity. Because, do you see that there's a contraction here, the mu's? Now, what do you know about the contraction between 2 things?
Invariant.
That's invariant. So that means that this part, excluding the nu, is invariant. So that means that this equation will hold in all observer systems. Now, of course, the nu part will change, because this will transform as a 4 vector. But we know what the rule is. So the reason to write it like this is that it makes extremely clear how to go from one guy's fields to the other guy's fields. That is much more difficult than here. Here that will be a nightmare to do the old transformations. What you would have to do is take these crappy things, substitute them in here, and then work the whole thing out. Much more difficult. Here, extremely simple. Contraction, so this part is already invariant. And the nu's, you know exactly how to transform via Lorentz transform. So this is why people in theoretical physics use that rule. Well, it takes us 5 weeks, but there you go. Main conclusion, a completely relativistic version of all of electrodynamics. Note, I never put in the special relativity. I mean, you know me, I like to repeat myself. Here's that point one more time. when we started with this, or even with those, the Biot-Savart-Nicaise, special relativity was already in there. It was hard to tell, because it doesn't look special relativistic at all. But all of this is just rewrite. I never have put any new physics in. The only thing I did was, well, take that thing, rewrite. Oh, wait a minute, it's completely relativistic. So that means that our starting point was already relativistic, but now it's extremely clear. You can immediately tell that is the case. So there we go. A couple of minutes left. We have some mop-up minutes maybe, or maybe there's a question.
Yeah, we don't have time to prove that ddx.
Oh yeah, let's do that.
Oh, yeah.
Okay? Because that was the point that we made before. I've postulated that the ddx is a contravariant 4-vector. We've never proven that. In the last 5 minutes we should be able to do that, because we now have our beautiful, beautiful, beautiful 4-vector notation, which makes life very simple. I will erase all of this. Okay, so the question is, if I have a function, a random function, and I want to take its derivative with respect to x primed, then what does this look like in some other guy's coordinate system? My claim is it will transform like a Lorentz transform. So that means, my claim is that I will find that one guy's derivative is a Lorentz transform of some other guy's derivative. Right? This is the shorthand notation for how Lorentz transform works between one guy's observable and the other guy's. So my claim is, if I can prove this, then I've shown that the derivative is a 4-vector. I haven't proven yet that it's a contravariant 4-vector, but I have proven, because of the Lorentz transform, that it is a 4-vector, that it transforms in the right way. Now, a random function will generally depend on x, y, z, and t. And I'm now taking its derivative with respect to x primed. But there's no x primed in there. But we've seen that you can write x's in other guys as x primes and t's and z's and such. So it's going to be crappy notation, but I cannot help it. This x will depend on the other guy's x. Do you agree with this? That this x is a function of the other guy's x primes? It just states that if you have one guy's x, you know how to write as the other guy's x. We know how to do it. That's the Lorentz transform itself. And very long notation. Well, let's write it out in full. So, there's that. Generally speaking, if you have a derivative, say you want to take the y derivative of this function, right? Forget for the moment about special relativity just as a calculus question. Somebody asks you to take the derivative of y of this thing, but the thing happens to depend on x, which depends on y. What do?
Chain rule.
So yeah, what would it be?
df over dy multiplied by
This small.
dx over dy, something like that.
This will be the chain rule. Okay? But suppose that this thing now depends not just on x, which depends on y, but also on z that depends on y. So that means taking the derivative will not just be this. Right, the derivative means I wiggle y a little bit, and the question is how much does f wiggle along? Now if I wiggle y a little bit, then my x will wiggle, and as a result f will wiggle, that's this part. But my wiggling of y will also wiggle z, which will wiggle f. Now that I haven't written down yet. Do you know from calculus what the more general chain rule would be in that case? Have you seen that before? If not, I'm just going to give it to you as a calculus rule. The idea, the general chain rule is, take this derivative of f with respect to all of their, oh, this is not a plus, comma, all of the separate terms. It's like this. This is the general chain rule. If you haven't not seen it, I mean, I'm sure you've all seen this one before. The general one looks like this. And for every other component, every other argument of f, you'll have to add another of these terms. Okay? Well, that's what we have to do here. Because I have an x, y, z, and t, and all of them depend on x prime. So I get this huge, huge chain rule stuff here. Because look, this one already gives us 4 terms via the chain rule. This one will give us 4 terms, that one will give us 4 terms, that one will give us a huge amount of terms. Man, that sucks. How are we on time? Because I'm guessing we're getting short.
Just go.
Okay.
Just go.
Okay. Here's my claim. Suppose that I take the mu derivative. Yes, that could be the time derivative, could be the x, y, and z derivative. Either of them. My claim is that then this derivative is the same as this. If you don't trust me, let me write this out. I've written a contraction. Do you see that? There's a contraction in u. So this is really just shorthand for df dt, and then dx dt, excuse me, that's dt, plus df dx 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 primed mu plus df dy dy dx primed mu df dz dz dx prime mu. This is just shorthand, yes? But do you recognize that this is just a chain rule? Just a second ago, I gave you as a calculus rule that if you find that this thing depends on multiple arguments, each of which depends on x mu, then the derivative would look like this. So from calculus, you know that this is really just this. And the only thing I've done was I squeezed it into our notation with the contraction. So it's just shorthand. And you can imagine why I like this one more than this. So I haven't, excuse me, I haven't done any physics, I just applied the chain rule and put it into our 4-vector notation. Huh. There's something beautiful happening here. Because what I see here is dx nu. Right, let's focus on this one just for a second. This is dx nu. For the purists under us, there is a slight difference between a curly d and a straight d. Forget about it for now, it's not important. Now I have to take a derivative of x mu with respect to x primed mu. Now that doesn't work. You cannot take derivatives of one guy's coordinates with respect to the other guy's coordinates. So what I would have to do is rewrite this guy's coordinates into the other guy's coordinates, because then I can take the derivative. Now, do you know how to rewrite a dx nu in terms of the other guy's coordinates?
Lorentz transformation.
That's a Lorentz transform. Like this, yes? You agree with this? Wait, my primes are wrong. It's an inverse transform. If you go from x, if you want to know x primed, you take the Lorentz transform of the other guys. I've now introduced an inverse Lorentz transform. But that means that this part, the dx nu, I can write like this. Oh, I have to be very careful. There's already a mu here. You see? And what I wanted to do was, I also had a mu here, out of muscle memory. Contractions I typically write with the mu's. But then I would have multiple mu's here. That's not too beautiful. This mu has nothing to do with that mu. This mu is because that's the derivative that I'm taking, and these mu's have to do with the contraction. So let's call this mu alpha, so not to confuse them with the other mu. I mean, I haven't changed this thing itself, right? I mean, it doesn't matter if you take alpha 0, 1, 2, 3 and add everything, or take mu 0, 1, 2, 3 and add everything, you still have everything added. So let's call these alpha. Question? What is this? I have some coordinate. Let's say it is t, alpha is 0, and I take the derivative with respect to x. Mu is 1. What is the derivative of t with respect to x? It's 0. Think about that for a while. Why that is 0. If I have, generally speaking, forget about relativity for a second. If I have this, I have x, y, and z, and they're independent components. The way somebody's moving in y direction has nothing to do with the way somebody's moving in x direction. Okay? And then I say, you know what, I'm going to take the x derivative of these three things. Now, if my y motion has nothing to do with my x motion, then y is a constant as concerns the x. So the derivative of the x derivative of these two things would produce 1, because it would be the derivative of x with respect to x, that is 1. This will be 0, and that will be 0. Apply the same logic here. I have an alpha, some value. And it takes derivative with respect to mu. Do you now see that if alpha is not mu, you're taking derivatives with respect to things that have nothing to do with each other, that will give you just 0? And that the only way that this derivative is non-zero is when alpha is mu, because this is when you take dx derivative dx, or dt derivative dt, or dy derivative dy. So my claim is, taking this derivative will only yield a non-zero value at the moment that mu is alpha. That's the only time that I take derivative of a thing with respect to something that is dependent on the same thing. And that derivative itself is going to be 1. But that means that this thing, this derivative, is sort of a thing that singles out a particular value of alpha, doesn't it? Of the 4 terms that you might have, it says, no, there's only one of them that will give you non-zero, and that is when alpha itself is equal to mu. But that means that this alpha must be mu. And then it gets multiplied by 1, because then the derivative will be 1. So this is this. We have found now, by you just using the chain rule, that if you want to take the x mu derivative primed of a function, any function, it's equal to Lorentz transform, the contraction of the Lorentz transform, times the unprimed derivative. That's what we have found, just by mathematics and the chain rule. And I hope you recognize that this is the defining property for a 4 vector. Four factor, what defines a four factor is any four numbers, if you go to one guy's coordinate system to the other, there's a Lorentz transform in between. We've explicitly proven that now. The only difference is, so I've proven out it's a four factor. That matter has now been settled. The only thing that I've done now is I had to apply the Lorentz transform in the reverse order. Right? Normally you go from x prime to x. I now went normally you go from x to x primed, and I now went from x prime to x. So that means you don't need the Lorentz transform, but the inverse Lorentz transform, the other way. And that makes it a contravariant four factor. And that was the claim that we still had laying around, the gaping hole in our theory. So the fact that there's a Lorentz transform in between tells you that the derivative indeed is a four factor. And the fact that you had to transform the other way in order to make the chain rule work tells you that it was a contravariant four factor. And this is why every time we did that, we transformed the derivative, we took a plus sign in front of the v. And I think that really concludes the argument.
Is there a difference in notation between a Lorentz transformation and an inverse?
Yes. Yes. The mu's and the u's are reversed.
Okay.
So what was the question again? The difference between
The notation of an inverse, if you write it as a Lorentz matrix, if there's a difference in notation between the two.
Oh, so you switched.
Yeah, the normal Lorentz transform would be like this. Would be that the alpha will be here and the nu will be there. And the inverse is this. All right, so that concludes most of what we had to do. Now, as you know, next week I won't be here, so Ronald will take over. It might be that Jacob might do some duties, but Ronald is going to do everything unless he passes something on to Jacob. There's no more physics. This is all the physics there is. So next week, what Ronald will do with you is apply these rules to different situations. So your question yesterday about the needle and such, we selected a couple of exercises that do exactly that. So you have a situation where you know the E fields and the B fields, and the question is use these rules to see how it looks like in the other guy's system and see how the E's and the B's work out. And Scott, that's also your question. That the question then is, how do the forces work out? And ultimately, I hope that you will see in those exercises that the forces themselves will not change. So even though the E fields and the B fields change from one guy to the next, directions change in all kinds of directions, but the F's will be exactly the same for all. So that means that the rules can be applied for all observers. So this is what Ronald will do. And he will spend some time to show you how this is embedded in the rest of physics. But physics-wise, as in there's no more physical content. Actually, we were already done with physical content in the first lecture when we got this. But we squeezed some relativity in. Now the exercises that Ronald will do with you, I will put on Eleum. I will also put the synopsis and the video. The video of yesterday, videos, small plural, I've already uploaded. So I think you should be complete. By the time, yeah. Any questions? Yes?
I have a question. Like
Sure.
if you go back to, we had like one matrix is like the F, like mu,
Yes.
and then you introduced a new one because you couldn't find out on the max calculations, but that's part I didn't get because like before you said like with mu 1, 2, 3 you get the 4 maximum equations.
No, you get the fourth maximum
Four.
equations. No, not all four, the fourth.
But why if we, because like before we took mu 0 and mu 3,
Yes.
so what happens if you take mu 2 and mu 1? Can you take it?
Mu or mu?
Mu.
Mu. We have already done it for this one. When we take what, mu?
That's so confusing.
Okay.
Like for this one we took 0
Yes.
and 3.
Yes.
But what happens if you take 1 and 2? Don't we get any maximum equations?
If you take mu, so this one 1 or 2 or 3?
Yeah, what we did is we took it for 0 and
Yes.
3. But we didn't do it for
No,
if
no,
it's
that's
1
2.
and 2.
No, okay,
So
no,
what
that's
happens
2.
if
Okay,
it have
good. I'm sorry, it's the mu and the nu. It has nothing to do with either of us. It has to do with these two symbols sounding almost exactly the same.
It's so difficult, like,
yeah.
to keep on track. Like, even like during the lecture, like sometimes you hear mu, and like,
Yeah.
it's too confused.
Maybe a nice mental note for next year for myself would to use not mu and nu as the contraction ones, but alpha and beta. So maybe that's a good idea. It is conventional to take mu and nu as a small amount of excuse for myself, but I do understand confusion.
No, but if you listen to that,
I'm sorry. That's I'll try to stick to alphas and betas from now on. We're stuck now with the nu's. So we did the nu is 3, and then we got the z component of the fourth Maxwell equation. We haven't done it, but if you take nu is 1 nu and nu is 2, you will get the x and y components of the fourth Maxwell equation.
Oh, okay.
So that's what I write here. Nu is 1, 2, 3 together give the full fourth all three components to the full. Yes. And then we found that if you take nu is 0, you get the first Maxwell equations. Still 2 Maxwell equations to go. We introduced, we already listed, but we introduced this one. You have to prove for yourself that it's a tensor, but it goes via the same way as we did for f.
And that is for mu or mu?
For nu. Yes. My claim is that if you do nu is 0 and nu is 1, 2, 3, I can already tell you what you will get. If you take nu is 0, you will get the second Maxwell equation.
Yeah, okay.
And if you take the 3 components, 1, 2, 3, you will get the 3 components of the third Maxwell equation.
Okay, makes sense. I was just confused, like by 4.
Yeah, I understand. It's fourth, not 4. Yes. And and in passing we introduced a new tensor, so I'm very happy. You have your own tensor. Okay, great. Again, on the lame I will put the exercises on. We'll do next time the videos and the synopsis of today. Okay, thank you for your time.
Thanks to you.
And see you in a week and a half.